Hello students, myself S.K.Jadhav from Department of Electronic Science, KTHM College, Nashik. In this lecture, we will discuss the topic NOT, NAND and NOR gates using MOSFETs. Let us understand the learning objectives of this module. After studying this, you will be able to understand the circuits of NOT, NAND and NOR gates using MOSFETs, that is CMOS inverter or NOT gate, CMOS NAND gate and CMOS NOR gate. CMOS inverter. Because of high noise immunity and low power dissipation, now CMOS logic families is most preferred in large-scale integrated circuits. CMOS inverter circuit contains both NMOS and PMOS devices to speed the switching of capacitive loads. It consumes low power and can be operated at high voltages, resulting in improved noise immunity. Let us discuss the working of CMOS NOR gate. NOT gate. Figure shows the basic CMOS inverter circuit. It consists of two MOSFETs in series in such a way that the P channel device has its source connected to plus VDD, that is a positive voltage, and the N channel device has its source connected to ground. The gates of the two devices are connected together as the common input and the drains are connected together as the common output. Here, these two gates, that is gate of first transistor, that is P channel MOSFET, and gate of second transistor, that is N channel MOSFET, is connected together and connected to common input, that is A, and the drain of first transistor and the drain of second transistor connected together, and the output is taken across the drain and the ground. Depending on the input value, only one transistor of the CMOS inverter will be on at a time. So, in both cases, there is no direct connection between power supply and ground, thereby reducing static power loss of transistor. When input is high, the gate of Q1, that is P channel MOSFET, is at 0 volt relative to the source of Q1, that is VGS1 is equal to 0 volt. Thus Q1 is off, and on the other hand, the gate of Q2, that is N channel MOSFET, is at plus VDD relative to its source, that is VGS2 is equal to plus VDD. Thus Q2 is on, and this will produce V out nearly equal to 0 volt as shown in figure A. That means when input A is equal to 1, then it produces the output, that is Y equal to or output equal to 0. Then in second figure, that means in figure B, when the input is low, that means A equal to 0, then the gate of transistor Q1, that is P channel MOSFET, is at negative potential relative to its source, while Q2 has VGS equal to 0 volt. Thus, In this case, Q1 is on and Q2 is off. This produces output voltage approximately plus VDD as shown in figure B. That means when input A equal to 0 volt, then it produces the output, that is output is equal to 1 or output is nearly equal to plus VDD or supply voltage. Then this figure shows the truth table of NOR gate or inverter. It shows when A equal to 0, that means at that time the P channel MOSFET, that is transistor Q1, remains on and the transistor Q2, that is N channel MOSFET, remains off, and it gives the output, that is output is equal to 1. And when A equal to 1, then high at the input makes the transistor Q1 off and transistor Q2 on, and it produces the output 0. CMOS NAND gate. Let us now discuss the CMOS NAND gate circuit. Figure shows CMOS NAND gate circuit with two input, that is input A and input B. It consists of two P-channel MOSFETs, that is Q1 and Q2, connected in parallel. Here Q1 and Q2, these two transistors are connected in parallel, and two N-channel MOSFETs, that is Q3 and Q4, are connected in series. P-channel MOSFET is on when its gate voltage is negative with respect to its source, whereas N-channel MOSFET is on when its gate voltage is positive with respect to its source. Figure shows the equivalent switching circuits when both the inputs are low. Here this figure B and figure C and also figure D, these are the equivalent switching circuits of CMOS NAND gate circuit. Here figure B shows the equivalent switching circuit when both inputs are at low state, that is A equal to 0 volt and B equal to 0 volt. Here the gates of both P channel MOSFETs are negative with respect to their sources, since the sources are connected to plus VDD. Thus Q1 and Q2 are both on. Since the gate to source voltages of Q3 and Q4, that is N channel MOSFETs, are both equal to 0 volt, that is VGS3 and VGS4 is equal to 0 volt. Those MOSFETs are off, and therefore the output is connected to plus VDD or high voltage through transistor Q1 and Q2 and is disconnected from ground as shown in figure B. Figure C shows the equivalent switching circuit when A equal to 0 volt and B is equal to plus VDD. In this case, Q1 is on because VGS1 is equal to minus VDD, and Q4 is on because VGS4 is equal to plus VDD. MOSFETs Q2 and Q3 are off because their gate to source voltages are 0 volt. that is VGS2 is equal to VGS3 is equal to 0 volt. Since Q1 is on and Q3 is off, the output is connected to plus VDD and it is disconnected from ground. When A is equal to plus VDD and B is equal to 0 volt. That means the third case, suppose A is equal to plus VDD and B is equal to 0 volt. Then the situation is similar. Actually, that situation is not shown here, but here you can consider A is equal to plus VDD and B is equal to 0 volt. Then the output is connected to plus VDD through Q2 and it is disconnected from ground because Q4 is off. And finally, when both inputs are at high voltage, that means when A is equal to plus VDD and B is equal to plus VDD, it is shown in figure D. Then MOSFETs Q1 and Q2 are both off and Q3 and Q4 are both on. Thus, the output is connected to the ground through Q3 and Q4 and it is disconnected from plus VDD. This table shows the operation of two input CMOS inverter NAND gate. That means when A equal to 0 and B is equal to 0, then A0 and B0 makes the transistors, that is P channel MOSFETs, on and at the same time N channel MOSFETs off, and it gives the output that is equal to 1. Again, when A equal to 0, then it will make the Q1 transistor on at the same time Q2 off. Similarly, A0 will make Q3 transistor off and Q4 on and gives the output 1. Then similarly, when A equal to 1 and B is equal to 0, Q1 will be off, Q2 will be on, then Q3 on, Q4 off, and it gives the output 1. But when A and B both are equal to 1, 1, then 1 at A input and 1 at B input makes the Q1 and Q2 transistors off. At the same time, 1 at A input and 1 at B input make the transistors Q3 and Q4 on and gives the output equal to 0. CMOS NOR gate. Let us now discuss the CMOS NOR gate. Figure shows two input CMOS NOR gate circuit. Here, P channel MOSFETs, that is Q1 and Q2, are connected in series and N channel MOSFETs, that is Q3 and Q4, are connected in parallel. Here Q1 and Q2 are in series and these two are P channel MOSFETs, and Q3 and Q4, these two are N channel MOSFETs which is connected in parallel. Then like NAND gate circuit, this circuit can be analyzed by realizing that a low at any input turns on its corresponding P channel and turns off its corresponding N channel MOSFET and vice versa for a high input. That means high at any input turns off its corresponding P channel MOSFET and turns on its corresponding N-channel MOSFET. P-channel MOSFET is on when its gate voltage is negative with respect to its source, whereas N-channel MOSFET is on when its gate voltage is positive with respect to its source. Here, this figure shows the conditions, that is, when A equal to 0 and B equal to 0, then A equal to 0 and B equal to 0 makes the transistors Q1 and Q2 on and Q3 and Q4 off, and it will give the output that is equal to 1. That means output is high or at logic 1 level. Then in this figure, A equal to 0 volt and B is equal to 1, or B is equal to at plus VDD, then 0 at A input makes the transistor Q1 on and Q2 off, and B1 at the B input makes the transistor Q3 off and Q4 on, and it produces the output low. Similarly, if if we reverse the case, that is A equal to plus VDD and B equal to 0 volt, then again it will give the output, that means 1 at A input and 0 at B input makes the transistor Q1 off and Q2 on, at the same time makes the transistor Q3 on and Q4 off, and produces the output 0. And in this equivalent circuit, when A equal to 1 and B equal to 1, that means when A equal to VDD and B equal to VDD, then 1 at the input A and 1 at the input B makes the transistors, that is Q1 off and Q2 off. At the same time, it makes the transistor Q3 and Q4 on, and it produces low output. Then this table shows the truth table of CMOS NOR gate, and when A and B equal to 0, then Q1 Q2 is at on state and Q3 Q4 at off state, and it gives the output that is equal to 1, and remaining all input states, that means A equal to 0 and B equal to 1. Similarly, A equal to 1 and B equal to 0, and also A1 and B1, it produces the output that is equal to 0, and therefore this truth table is equivalent to truth table of 2 input NOR gate. That means we can say that for NMOS transistors, if the input is at one state, the MOS or MOSFET turns on, otherwise it is off. And on the other hand, for the PMOS, if the input is 0, the MOSFET switches on, otherwise the transistor is off. That means if either of the input is 1, the output voltage is equal to VDD. Then in this lecture, we have discussed the circuits like NOT gate or inverter by using CMOS, then NAND and NOR gate by using CMOS or by using N-channel and P-channel MOSFET. Actually, logic gates are manufactured by using a range of logic families, and both MOSFETs as well as bipolar transistors are used in logic family. But most widely used logic family is CMOS family, and CMOS is available in a range of forms offering very high speed or very low power consumption. Thank you.